Resident Evil 3 Mercenary Mode. Of course, it was a very fun, playable sort of mode in the original Resident Evil 3. And of course, in a remake, they, decided to not include that, among other things as well. Of course, in Resident Evil 4, they made that remake much better, and they included mercenary mode in that game, but it doesn't matter. Of course, the nostalgic one for me, my first ever PlayStation 1 game, of course, that one they had to mess up. Anyway, welcome to CS302 Assignment 7, and we're going to be implementing this Resident Evil Mercenary leaderboard using a priority queue. So, if in case you never played this mercenary mode, basically what it is in Resident Evil 3 at least, you have you pick a mercenary and you have to sort of basically go through the city, Raccoon City. You have to go through Raccoon City, and you have to battle against various monsters, and you have to save civilians. And of course, you get point totals every time you defeat monsters and save civilians. Now, for this implementation, we're not going to be using Resident Evil 3's time-based system. We're going to have a hybrid of Resident Evil 3 and 4, where you get points for every time you defeat an enemy. So let's go ahead and talk about how we categorize each monster in the game. So, of course, we have, zombies. So every zombie that's defeated, you have to, of course, have multiple counters for every mercenary. And of course, you apply these multipliers to each counter. And of course, you have to sum all these up to compute each mercenary score. So you have a zombie, and of course, Resident Evil was already terrifying enough, but to make things worse, let's add giant tarantulas in the game. So you have spiders, drain demos, zombie dogs. Now those ones were always tough to defeat. Hunters, they're always sort of relatively scary enemies. Nemesis, he would always appear as one of the enemies in mercenary mode. And of course, you can rescue a civilian. So you have multiple counters you would have. So you're going to, of course, for every mercenary, you're going to use a struct to maintain each of these counters. And to compute each score, you just sort of apply these multipliers to every count of these categories. You sum them up, and that's going to be the complete and total score. So anyway, we'll get into the struct in a bit. But let's go ahead and now talk about the PriorityQ class. Alright, so here's your PriorityQ class, and I also named it this way on purpose because there is a priority underscore Q type in C++, so using this name will not cause any ambiguities and won't, accidentally allow you to include the STL PriorityQ. So anyway, for PriorityQ, let's first talk about the private members. So we have, of course, this vector heap array. Now, this priority type, each element of our heap array is of type priority type, and our priority type contains a key and priority, or you can say our key value pair. So essentially for our mercenaries, T1 is going to be really a string. We're going to have a mercenary name will be a string. And T2, that's going to be that struct MercType, which I will talk about after I discuss the PriorityQ class. So you're going to have this priority type, and each element of heap array will be of type priority type. So this, of course, this is going to be the array that maintains the max or min heap, but I would suggest a max heap would be the best idea for this program. Now, we have this unordered map right here. Now, I guess this is my mistake. So in class, when we were doing PriorityQs this semester, I forgot to go over IncreaseKey and DecreaseKey. But luckily, I can discuss that in more detail after I cover the MercType. When I go over the BubbleUp and BubbleDown functions in more detail, I'll go over what this item of the PQ is used for. But for now, let's focus on just the heap array. And then we have, of course, our priority type. Let's look at our default constructor right here. Now, for the implementation of our heap array in class, I would have index 1 be the root, index 0 will be a throwaway element. So it's up to you how you want to create your priority queue. So for the constructor, If you intend on having index 0 be your root, then the default constructor doesn't do anything at all. However, if you want to have index 1 be the root, then this default constructor does have to resize the heap array by one element. So that way you have the index 0 element is there, and then from now on, after you push back every time, it will push back from index 1 onward. So it's up to you how you want to do that. If you do use 0 as your root index, you'd have to, of course, modify those those formulas to compute the left and right child indices. Slightly modification, but it's up to you how you want to do that. But anyway, it's going to be your default constructor. Pushback, well, we're passing in sort of this, the key and the priority accordingly. So of course, within this pushback function, you have to create some temporary priority type object, assign this parameter into the key field and this parameter into the priority field, push that object back to the back of the heap array, and of course call BubbleUp from that last index that you just pushed back to. So nothing too crazy there. Pop front, remember how that works. To take the last element of your heap array, you overwrite the root with that last element, you do a pop back from your heap array, and then bubble down from index 1 or 0, depending on which index you choose as your root item. Increased key, I will discuss that in a little more detail later on. I go into more detail BubbleUp and BubbleDown functions. Get front priority, this one's simple. Return the root element's priority field. And for get front key, return the root element's key field. That's it. Bool is empty. Return true if your priority queue is empty, and false otherwise. And I think that, I guess that covers the preliminaries here. I'll go into BubbleUp and BubbleDown in a little bit, and I'll also go into how this item to PQ map can be used with BubbleUp and BubbleDown. So let's go ahead now discuss the MercType content. Okay, so here's the MercType. Now I know I am kind of bouncing around in the PDF a little bit, but let's go talk about just this part of the main, which is going to be the MercType we're going to be implementing. So we just maintain these counters. So this is going to store for each mercenary how many zombies they defeated. I think I spelled mercenary wrong right here on that comment, but it's okay. So how many zombies they defeated, how many spiders, drain demons, and etc., and of course how many civilians they saved. So these values together, using those multipliers we had above, we can use that to compute the mercenary score. Now, I'd recommend implementing a few of these in the class. So maybe the constructor, this will be a lot more nicer. So of course you can sort of set all these to 0 in the constructor. So whenever you're pushing, initially we push all the mercenaries into the priority queue. You can of course push a mercenary name followed by an empty or by default object. Now right here, you do want to implement some type of comparison operator. So less than, greater than, less than, equal, whatnot. Now, before I go in detail, do not actually try to overload the question mark operator. There is no such operator in C. Well, there is a question mark, but it's a ternary operator which you cannot overload, I don't think. And of course, it would not make any sense even for this program. So that question mark is just sort of, I guess, sort of open for you. So if you want to overload less than or greater than and so forth, be my guest. And of course, you can overload more operators as needed. So for the increase key, you may have to actually update a mercenary by adding amount of zombies or adding the updated amount of zombies they defeat and so forth. And you have to overload these maybe a plus or a plus equal operator. Now the purpose of this is because inside of the PriorityQ class, you don't want to do anything specific. So for example, in the heap array, you have a heap array, and of course you're going to have heap, what was the actual? Let me take a look. a priority type. There we go. So T1, now it's going to be a string, and T2 is going to be um, a MercType, but you can't assume this. You have to write your code with this notion that you don't know what T1 and T2 really are. So the thing is that if I were to say something like heap array index 0 dot priority dot zombies, that would make it too specific to the MercType. At that point, if you were to do that, you may as well just not write your program with templates. And that would be crazy talk. Of course, you want to use templates because you want to learn. We want to reinforce templates in this class. So for that reason, if you have to update, let's say within a heap array, you want to update index 3 mercenary zombie amount, you can't say heap array index 3 dot priority dot zombies plus 3. You can't do that. You have to actually, I can give you some hints as to how to do that in the increase key function, but you don't want to do something like that. But anyway, that's going to be the priority type for the priority queue. So you can see here, you're going to implement the following structure. Now, the rest of this main has some more stuff here, but I will go ahead and I will go over this in more detail in a little bit. So now I want to go ahead and talk about the BubbleUp, BubbleDown, and of course the IncreaseKey functions. Okay, so let's go ahead and discuss BubbleUp and BubbleDown. So as you know, when we bubble up from an index in our priority queue, and of course bubbling down, same idea, bubble down from some index. So suppose we just recently inserted Mikhail to the back of our structure. And of course, Mikhail, you have to give a shout out to him because he sacrificed himself to save Jill and Carlos from Nemesis on that train scene from the original game. So we push back Mikhail, and then we have to bubble up from index 6, or from the last index we just inserted from. Now below we have this items to PQ map, and I'll just kind of give you an idea of what you're supposed to be doing here. But the idea here is this is going to be more needed for the increase key function, but the purpose of this items to PQ is to map us which index each mercenary is on. So for example, if I take items to PQ and I use the bracket operator on Leon, it returns the value 1, telling me that Leon's at index 1 of my priority queue. If I were to apply my priority queue on Carlos, then if I apply this unordered map and pass in Carlos into the bracket operator, it returns the value 4, telling us that Carlos is at index 4 of this priority queue heap array. So anyway, once we insert Mikhail, we have to bubble up, and of course, bubbling up, our index will currently contain 6. And of course, the parent index is going to be just simply 6 divided by 2, or index divided by 2. So we have to compare Mikhail with Claire. So, of course, I'll give you sort of the, I'm not going to write the entire code here, but I want you to think of it like this. So you're going to have heap array at index 6 dot priority. So we're going to actually prioritize everything by priority. The key's only purpose is just to have, the name of each mercenary, but the priority, we're going to be arranging this priority queue by priority. So I would go ahead and compare this priority with the parent. Now, this comparison operator right here, that's actually the overloaded comparison operator for the MercType, because priority, that's going to be a MercType, whereas the dot key, that's going to be a string type in this scenario. So I'm using the MercTypes comparisons. That MercType comparison operator is going to, of course, compute the values, the score of heap array 6 and heap array 3. If heap array 6's score is bigger, then this returns the value true. If it returns value true, then we have to swap these two values in this heap array. which is a very simple to swap these. You can use a swap function built into standard library. You can use standard with the scope operator swap. You can even, I mean, I can give it to you right here. You can just do this. You can just call swap and just pass in heap array 6, heap array 3. You can use that swap function, which will swap those two values in this structure. And then you also have to swap essentially these two, because you have to also swap these as well. Because after you complete the swap, what's going to end up happening is that Mikhail is going to now be at this position. And of course, we copy the priority as well. And of course, Claire would go right here. And also we also would swap the priorities as well, but the swap function will take care of that for us, just like that. Then we'd have to swap these as well. Because now Claire is now at index 6 of my heap array, and Mikhail is at index 3 of my heap array. So you have to, of course, just swap two structures. You have to swap the heap array, and you have to also swap the two elements in the map. And of course, after you update index to be 3, and you would, of course, continue this process until eventually you hit the root, or once the parent is larger than a child, there's no need to bubble up any further. So just like in class. So that's how you bubble up, essentially. Let's say, for example, so now next phase, let's say you want to now go over BubbleDown. BubbleDown will mostly be used for when you do a pop front on your heap array. So suppose you do a pop front. So pop front, which is going to be our deletion, is going to just basically take the last element of my structure, which currently will just be Claire in this case. It's going to overwrite Leon with Claire. And also is going to overwrite the priority with Claire's priority. Then it's going to pop this off of my queue, which of course you want to also update Leon. So then first update Claire's index to now be 1 because we moved Claire to 1. And you want to maybe assign Leon. Either you can remove Leon from the map completely, or give Leon a value of 0 or -1 that tells you that Leon is not in any element in this heap array. And then you have to bubble down. So of course, remember, we have to compute the two children. So we bubble down from index 1. And you have to compute the two children, which will be right here and here respectively. Of course, you want to figure out which is the bigger child. Is it Jill or Mikhail? Let's just happen to say that Mikhail is the smaller child. Let's just say for right now. We compute that index 3 is a smaller child, and the same idea. We're going to just compare the heap array index 1. Oh, sorry, index 3. My mistake. Index 3 dot priority larger than heap array index 1 dot priority. Again, same idea. You could actually do this. Let me just give this to you. You could have actually done heap array index 3 dot priority dot zombies. You could do that, but again, just to remind you, you don't want to, because you want to make sure your class is generic. So that's why you want to just use the priority object, which is going to be a MercType. You want to use its comparison operator, see which mercenary has a higher score, a bigger score, and the bigger score will get bubbled up, or bubbled down, or in this case, if index 3 is larger, you have to bubble index 1 down. So of course you have to just simply swap these two elements in the priority queue. Yep, priority queue. You want to swap these two, and also you want to swap these two, because after you complete this swap, Claire is now going to be at index 3, and Mikhail will be at index 1. And of course, after you do that, you update the index to this new position, index 3, and then you continue this process until finally either you hit a leaf, or both children are in fact both less than the parent, you can stop bubbling down. So that's sort of how the BubbleUp BubbleDown works. So hopefully this makes sense. And of course, I hope the items to PQ map, you can understand what we're doing. But all we're doing is we're just going to take the key, the mercenary name key, and we're going to map it to an index. We're going to map it to a number, and that number tells you which index and heap array that element resides in. So again, just to remind you, if I take items to PQ, bracket Chris, it returns the value 5, which means that Chris is at index 5 of my heap array. Okay, so last complicated part is going to be the IncreaseKey function. Let's go ahead and discuss that now. Okay, so the IncreaseKey. Now for priority queues, there's typically a function, IncreaseKey or DecreaseKey. Now, let me give you a sort of a backstory, or I guess what's the purpose of IncreaseKey or DecreaseKey. The purpose is this. So when I mentioned the example in class, when I talked about a hospital line could be a good way of thinking about how priority queue works. So when you insert somebody to the back of the line, and of course, based on their condition, they can bump up in the line if their condition is much more severe than somebody else's. So the idea is, well, let's say we have, you know, people in line in a hospital, and while they're actually in line, they're already in the priority queue, but someone's condition gets worse while standing or while being in line. Then of course, we want to update that person's priority, whoever's in the line, and then bubble them up or bump them further in line. So that's sort of the idea for this. So let's say we call this function IncreaseKey, and I'm passing in the key and the priority. So this is going to essentially be, in this example, this is going to be, let's say we have, it's going to be Carlos, let's say. The key will be Carlos, and the priority, this is going to be added to Carlos's priority. So now typically for increase and decrease key, you simply just reassign the value. But in this situation, we're going to add this to Carlos's priority in the heap array. Now, the first step is you have to first find Carlos in a heap array. So if let's say we didn't have an items to PQ map, how could you find Carlos in this heap array? And the obvious answer would be, of course, linear search this heap array until you finally find Carlos. Once you find Carlos, you add this parameter, you add it and add it to this priority and update with this amount. And then of course, bubble up. Now, the runtime to first find Carlos would take O of n, and then O of log n to bubble up. So the runtime overall would be O of n. But what if, instead of linear searching, I can use my items to PQ, so I could do something like this. Items to PQ, pass in that key, which I can just sort of put this right below. In reality, let's suppose the key happens to contain Carlos. So key would be just Carlos in this case. This will return the value 3. So then we can just simply go to index 3 of the heap array. So guess what the runtime of this would be? Well, this would be constant. So in constant time, we can find out where in the heap array Carlos is. And then we can add this priority parameter. We can add it to this and then bubble up from index 3. And bubbling up takes log of n, so it's O of 1 to first find Carlos plus O of log n to bubble up. So we improve the runtime from O of n to O of log n using an unordered map behind the scenes. So what's going to happen is use unordered map to first look up where in the priority queue is this key. Once you find it, of course, let me just go ahead and return. Maybe I'll just sort of just return I, so I'm going to have maybe I equals this, let's say. And I would just do this. I would just say heap array at index I dot priority plus equal priority. Now, of course, if you didn't overload the plus equal, you can of course do heap array I dot priority equals heap array I dot priority plus priority. You can do that as well, but I implemented plus equal to make it easier. But you can of course just use a plus operator. You'd have to just do heap array I dot priority equals heap array I dot priority plus priority. That also could work. Either one is fine, but plus equals a bit of a shortcut, I suppose, but not a big deal. So anyway, I probably should just keep that. I should maybe undo that. I'll just put that back. There we go. So what's going to happen is we use a PriorityQ to update, and then of course after we update the value, we bubble up from index 3. And of course that's the same exact idea. You compare Carlos to Jill, because Jill was the parent in this case. And of course, if Carlos's value is larger with the updated priority value, then we swap Carlos and Jill, and swap Carlos and Jill in this items to PQ as well. So it's kind of a quick explanation to that. So I hope that sort of gives you an idea. But the purpose of this is just so we can update an element that's currently in the priority queue. Using this unordered map, we can, in very fast time, can update an element, which we will see this example used in other. So we're currently on graph theory, so we'll see this actually used in various graph theory algorithms. Okay, so now let's go ahead and do a sort of an overview of main, and then I think we should be done at that point. Okay, so I went over the beginning part of main, the MercType, and how you want to, of course, have a priority queue of MercType. So the first thing we're going to do is, in our main, is we're going to be given an input file. This input file contains all the mercenaries' names. Let me go ahead and open this up for you so you can see, but I will provide this, of course, to the on Canvas. Now, of course, no spreadsheet file, an ordinary, regular sort of file like this, and we contain all the names of all of the possible mercenaries. So all we have to do is one by one, just push each mercenary onto our priority queue. So of course the key will be the name, and then the priority, that value, we're gonna pass in a default MercType object. And of course, since we actually overloaded or we implemented our own custom constructor, our default constructor, you simply pass in the name red, comma. You can use the default constructor as an actual parameter. It will pass in a default argument, and it will just simply push them all into our priority queue. So which element will be at the very top is not really relevant because it's going to be a tie at this moment. So we're not going to really focus on that right now. But of course, we just simply push these into our priority queue. And now, of course, we're going to simulate our mercenary mode sort of program. So now what's going to happen is once we put those in, we're going to have our second input file. And of course, this input file is going to be our simulation file. So we're going to have mercenary name, monster name or civilian, and then an amount. So let me show you the input file that does provide. So there's several of them. So I'll go over simulation 1. So each line is going to have the mercenary name. So I guess Ethan from Resident Evil 7. So do Ethan, a space, and then zombies 1. So Ethan took out 1 zombie. And then the next line contains Claire. So Claire saved 10 civilians. Ethan, next line, Ethan defeated 3 drain demos. Louise saved 10 civilians. Ethan defeated 2 zombie dogs, and so forth. So each line of this file, you have to parse this line, but it should be very easy. There's no comma separated, so you can just easily use the input operator to simply separate these three components. So all you have to do is you read in the name, the zombie amount. So of course, what you can do is you can create a temporary object, a MercType object, and then have the zombies amount for that MercType object to be 1. Then you call IncreaseKey. You pass in the name, and you pass in a MercType object that contains only one zombie. And then this object will be added to Ethan's priority in the priority queue. And then let's look at the next line. So Claire civilians 10, I have to update Claire in the priority queue by reading in Claire. I'm going to just create another default object of MercType. I'm going to assign 10 to the civilians field of that MercType object. The rest will all be 0 for that MercType object. Then we call IncreaseKey, pass in Claire. Then we're going to pass in a MercType object that contains 10 for its civilians amount and 0 for everything else. And of course, within the IncreaseKey is going to update Claire's priority by adding, 10 civilians and so forth. So every line is going to cause you to call IncreaseKey, which is going to, of course, update the priority queue after we have one of the mercenaries updates. That's all we have to do. And then we're going to do this until end of file is read. And then for the output, all we have to do is every time we have a new leader, update that leader, output that name of that leader and their current score. And you just keep doing this. And once you hit end of file, you simply output the ranks of each mercenary. And that's basically it. So let me give you sort of a sample output. So there's specifications, so you can read this on your own. I compiled my main, so I have a PriorityQ.h file, but remember it's a template file, so I include PriorityQ.h into my main. My PriorityQ.h contains my PriorityQ declaration and implementation, so I have to only just compile main because I include that PriorityQ.h file. I run it. I'm going to have mercenaries simulations 4. So I enter mercenaries file as mercenaries. I use the 4th simulation file. And we can see here every time we have a new leader at any point, we output the mercenary's name followed by their score. So we can see here. So of course, we have Krauser. Ada gets ahead of Krauser. Let me see. Then we have Leon and Krauser fight. Okay, that makes sense. That really does. This actually was a random file I created, but it happened to come out nicely. It came out to be, well, Leon and Krauser were battling it out, which it does make sense. Of course, Ada comes in there to, of course, help out Leon because we all know that Ada really wants to help Leon. She wants Leon to succeed, so she's kind of helping out by taking the lead from Leon, but at least that way Krauser won't be in the lead. That's what's going on there. But Krauser takes the lead back. Leon and Krauser duel it out, and of course, at the end, Leon's the last leader update. So at this point, we have end of file, and we output the rank of all of the mercenaries, and of course, Leon wins, which does make sense. So even randomly, it came out the way it's supposed to have come out because Leon, of course, has to win at the end. So that's about it. So hope this video did help you. So I guess happy coding, and until next time.